Once again, welcome to Adistar Lectures on Electronics and Optics. You have seen the highlights, and those are the things that I am going to discuss in this particular lecture. An ordinary comparator and a special type of comparator, both of them are designed using operational amplifier. At the end of this tutorial, I am going to tell you a new open source and the free software that will be helpful for scientific plotting and many other plotting you can use for plotting any type of data. So that's the software I have used during my PhD, and I have published many papers on this particular software. So that's the thing I'm going to share with you. So for that, please stay tuned till the end. Now, state on your screen, that is the ordinary comparator based on the operational amplifier. What an operational amplifier does? It amplifies. It amplifies what? Because it has two terminals. One is the plus terminal, another is the negative terminal. So plus terminal is generally called the non-inverting terminal, whereas the negative terminal is called the inverting terminal. But which signal the operational amplifier amplifies? The signal that is being applied to its plus terminal or to its minus terminal? The answer is none of them. It amplifies the difference between them, and that's why, as you can see, we can directly write this input-output relation through this equation. A is the gain of the operational amplifier, and Vi is the input signal that I have applied at its plus terminal, and the Vref is a DC voltage that I have applied to its minus terminal. The main purpose to express this equation is to show you that basically the output of an operational amplifier is nothing but the product of its gain, which is the A over here, times the difference between its two terminals. So basically, it signifies that operational amplifier amplifies the difference between its two input terminals. Fine. Now, if you study the ideal characteristics of an operational amplifier, you will see that this gain I for an ideal operational amplifier goes to infinity. Now, what are the consequences if this gain goes to infinity? Consequences are pretty impressive, because if this open loop gain goes to infinity, then how can I express this difference Vi minus Vref? We can express that this Vi minus V reference is equals to V naught divided by this gain. It's very simple expression. Now, for an ideal operational amplifier, this is not tends to infinity, this is equals to infinity. Okay. If so, then this goes to 0. I mean, this one. V naught divided by A. And we can directly write that Vi minus V reference is equals to 0, or in other words, we can write Vi is equals to V reference. So what does it mean? It means that an ideal operational amplifier can amplify a zero difference signal, even if the individual voltages are 0. That means if Vi and V reference both will be 0, then you can get a finite output. But for a practical amplifier, the gain becomes very, very high, of the order of 10 to the power 5, 10 to the power 6, or even 7. So if I take an example that A, I'm assuming that it is 10 to the power 6, and Vi, which is applied at its plus terminal, is a bit less than the reference voltage. So I'm assuming that V reference minus this delta, where this delta tends to 0, very small amount of Vi, the input voltage, is less than the reference voltage by a very, 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 very small amount. Then what will happen if A is not infinite, but it's a finite one, but it's a very high gain, it's out of the order of 10 to the power 6. In that case, you can write that V naught is equals to 10 to the power 6 times, if I replace this Vi by Vref minus delta minus Vref, or the reference voltage. So they gets cancelled out, and you are getting 10 to the power 6 minus 10 to the power 6 times this. So small difference in the voltages between its two terminals. So if Vi becomes less than 0.2 volt than the V reference, then you are going to get minus 10 to the power 6 times 0.2, and now you can imagine what voltage you can get. But it's not possible, because if it is possible to get a 200 kilovolt out of a simple operation amplifier, then probably I think you can take a 1.5 volt battery and an operational amplifier and you can run the entire railway system for that. So easily you can imagine that it is not possible. But why it's not possible? Because the every operational amplifier, not only operational amplifier, every kind of devices uses some supplies. So here the supplies are not shown, but in general the supplies are appeared at these particular positions. So these are plus VCC and these are called minus VEE. For a general purpose operational amplifier, these supplies are 10 volt, 12 volt, plus 15 volt, minus 15 volt, like this. So you cannot get the output voltage more than its supply. So whatever the calculated value you are expecting, but you get the maximum value close to that supply. So that's why we call them VSAT, SATs for saturation voltage. So whenever the input voltage becomes very less than the reference voltage, in this case that is the V reference, so we are going to get V naught is equals to minus V saturation voltage. In a similar manner, you can prove, or if I consider that Vi is greater than slightly greater than the reference voltage, then we are going to get V naught is equals to plus V saturation voltage. For an ideal operation amplifier, this transition takes place instantly, but for non-ideal operational amplifier, it doesn't take place instantly. Following this principle, if you apply sinusoidal signal as I have applied over here, where the reference voltage I have applied some positive voltage, as you can see. So whenever the input voltage is less than the reference voltage, so input voltage, this voltage is less than the reference voltage, and this reference voltage is connected to its negative terminal, so the output is going to saturate to the minus Vset. That's why within this range the output is at minus Vset, and when the input voltage is just crossing the reference voltage, output is instantly switching to plus Vset value or the plus saturation voltage, and in this fashion it's continuing up to the until the signal exists, input signal exists. But this is not the case with the practical operational amplifier, because the practical operational amplifier, that as you can see, you need to apply some finite amount of voltage as shown over here. So it's unlike these ideal operational amplifier, where this transition takes place instantly. Here this amount of voltage you need to apply, and thereafter the output switches to the plus Vset. In a similar way, when you apply the this difference, a finite difference along the negative direction, then only output can switch to the minus saturation voltage. And this happens if your operational amplifier has no offset voltage. But with this offset voltage, you are going to get that saturation at this particular point, where this is the amount of offset voltage, and thereafter you have to apply that finite amount of voltage, that what you were applying during this position when there was no offset. So these are the cases for the non-ideal operational amplifier. And one more thing I should mention, that this happens by considering that the signal that I have applied to this plus terminal and the reference voltage that I have applied to the minus terminal. But what if you interchange these terminals? That means the reference voltage will go to plus terminal and the input voltage will go to the minus terminal. Then the entire scenario will be reversed. So in that case, it will switch to along this direction and it will switch along this direction. So these are the theoretical part. Now I'm going to show you that how such kind of characteristics are varying with respect to the time varying signal. As you can see on your screen, the time evolution of the ordinary comparator. Here the input signal is applied over here. This one is the input signal of 1 kilohertz, and this is a simple voltmeter that is measuring the input signal over here, and the reference voltage that I have applied is 0 voltage. So that's why, as you can see, both the half cycle, both the plus and minus, they are coming of equal width. And since the input signal is applied to the plus terminal, So when the input signal becomes greater than the 0 voltage, so this is the 0 volt line, this one is the 0 volt line. So whenever the input voltage is greater than the 0 voltage, your output is switching to the plus saturation voltage, which is close to the plus VCC. Here I have used 15 volts plus minus 15 volt as the plus VCC and minus VCC. And when this input voltage is changing less than the 0 voltage, it is the output is changing to the minus voltage. So this is a simple time evolution of for this ordinary comparator, and I can easily show you there that the transfer characteristics that you have seen in a theoretical explanation. So that is, this one is the output transition, and if I show you the input, as you can see, as the input is varying, the output is changing. And since this operational amplifier is not an ideal one, so you are having this particular slope. This slope I'm talking about, this one, as because it is not the ideal operational amplifier. Well, now what will happen if I increase the reference voltage? So I can show you over here. Well, as you can see, since the input voltage, since the reference voltage I have changed, when the input voltage is reaching 4 volt more than the 0 voltage, then the output is switching to the plus Vset. This particular point is the 4 volt. So 4 volt more than the 0 voltage, and then only the output is switching. But this particular comparator has a severe limitation. So what is that? So for the demonstration purpose, I have applied this bunch of sources. So these sources basically generates this bumpy nature of the input signal. So it basically signifies there that the input signal is perturbed by some kind of noise, and that noisy signal can make this transition unwantedly. So this is a severe limitation for an ordinary comparator, and that's why we use Schmitt Trigger. Look at that. The same set of signal I have used over here, and I have produced that bumpy nature of the input signals to signify to represent the perturbation of the noise, and the output from the Schmitt Trigger, you are having a smooth transition from the minus VCC to plus, or minus Vset to plus Vset, or plus Vset to minus Vset. So this is the beauty of the Schmitt Trigger, and that's why Schmitt Trigger is a better comparator compared with the ordinary comparator. As you can see, the circuit over here, the only modification of what I did, that I have connected two resistors from the output of this operational amplifier, the same operational amplifier that I have used for designing the ordinary comparator. Here I have used the same operational amplifier, and I have connected one resistor. This one is the one resistor, and this one is another resistor. As a result, the potential across this resistor is basically appearing as the reference voltage to its plus terminal. Well, so such kind of configuration basically is providing a positive feedback to this particular operational amplifier, which is increasing its gain further. The advantage of such a positive feedback is that in this particular case, we are going to get the reference voltage depending upon the output voltage. And as we know, for an operational amplifier, the output voltage can change either to plus Vset or to minus Vset. So this level is the plus Vset level, and this one is the minus Vset level, as you can see over here. So now, whenever your output voltage is the plus Vset, so this is the reference voltage, I can write is Vref. So V reference voltage can be, if I assume this resistor, this one is R2 and this one is R1, then I can easily write that V0 times R2 divided by R1 plus R2. So this is going to be your reference voltage, and it's going to depend upon the output voltage. Now, as the output voltage has two states only, the plus Vset and the minus Vset, so you are basically going to get two reference voltage, which was not possible in case of the ordinary comparator. So when output voltage is plus Vsat, you are going to get this plus Vref is equals to plus Vsat times R2 divided by R2 plus R1. And similarly, when the output switches to the minus Vsat, you are going to get minus Vsat, or that is equals to the minus V reference times R2 divided by R2 plus R1. And this one is the advantage of having two reference voltages. So first one is that when your input voltage is changing from some negative direction to the positive direction, in that case, the output voltage is maintaining this plus Vsat level until this input voltage is reaching this UT stands for the upper threshold, and upper threshold is referred as the plus V reference voltage that I have shown you. So whenever the input voltage will be just greater than the upper threshold voltage, output jumps to the minus Vsat. And when the output switches to the minus Vsat, right now this threshold voltage gets vanished and establishing the new threshold voltage. So that is this one. Right now, you don't have this plus reference voltage. Instead of that, you have this negative reference voltage, that is I have denoted as the lower threshold voltage. Lower threshold is corresponding to the minus V reference voltage that I have shown you. In order to change the output state from the minus Vsat to the plus Vsat, the input voltage must cross this negative value. And this is a very significant one, because as you have seen that due to the perturbation of some noise, when the input signal was during its positive half cycle, then also the ordinary comparator, the state of the ordinary comparator gets changed. But here, due to the presence of the noise during the positive half cycle or during the positive amplitude of the signal, that means around this side, the output is not going to change, because right now the reference voltage gets shifted to the negative side. On the other hand, in the case of ordinary comparator, the reference voltage was fixed at a 4 volt and we don't have any scope to change that one. So whenever the noise was changing the amplitude level and that was coming below the 4 volt, so you got the change of the output states. So here it is not possible. So that's why we're gonna get a stable output voltage, stable change of states when we are using the Schmitt trigger. And this particular diagram is called the hysteresis of the Schmitt trigger. This expresses the entire phenomena when the input signal is moving from the negative direction to the positive, and the output gets changed when the input signal crosses the upper threshold voltage level. And during the negative transition of the input voltage, the output can change only when the when the input voltage becomes less than the lower threshold voltage, and this is called the Schmitt hysteresis. So what you are seeing right now, this is the Schmitt hysteresis. From the negative to positive direction, this output is changing at this particular position, and from the positive to negative direction, this output is changing following this particular path. Now, you can change the width of the hysteresis by changing the value of this resistor. As if I change the value of this resistor, I can increase the width of the hysteresis. As you can see it over here. Here I have changed the value of the input voltage to show you the width of the hysteresis by changing the resistance. If I change this resistance further to 3 kilo ohm, as you can see, the width gets changed further. And if I change to 1 kilo ohm, it gets reduced. So in this way, you can change the width of the hysteresis and you can adjust the reference voltage, and using which you can get a pure noise-free output, which was not possible using the ordinary comparator. Yeah, this one. So although the noise and bumpiness of the input signal exist, but still we are having a pure square wave. So here the Schmitt trigger using operational amplifier on LTspice platform. As you can see here, I have connected additional voltage source to provide a further reference voltage, and that is also possible using the Schmitt trigger as I did for the ordinary comparator also. So here, in addition to your feedback that I have established using this R1 and R2, if you want to change the width of the hysteresis without changing the value of the resistors, then you can add an additional voltage source. So that is also another freedom that we can use over here. Anyway, so I'm going to run, and I have applied the 5 kilohertz signal, sinusoidal signal. This is the input signal that will be compared with the reference voltages. So this one is the output voltage, and as you can see, the output voltage is changing at this particular position as well as in this particular position. So during this position, it remains at the minus Vset, and during its negative half cycle of the input signal, it remains at its plus Vset, which is just opposite case that I have explained using the ordinary comparator. Because just look at these post terminals where I have applied these connections. So the feedback I have applied to the plus terminal, whereas the signal I have applied to the negative terminal. So obviously the output will be reversed to that one I have explained using the ordinary comparator. Anyway, so right now I'm going to get the hysteresis data from this LTspice, and I'm going to plot that data on that free and open source software that I'm going to tell you. And to plot that, you need DC sweep analysis. Okay, and I'm changing this one to none to make it a DC value V3, and I'm going to tools, no, not tools, edit simulation command and DC sweep analysis. And here I'm going to set this as V3. Type of sweep is linear. Start value should be say -5 to +5, and increment is 0.1 for better resolution. Now if I check the output, as you can see, the reference voltage here, the supply voltage I have used as 10 volt, and the resistor I have used as 2K. This V4 voltage source, this is a 0, so 2.5 volt. And now let's see whether this transition is taking place at 2.5 volt or not. Obviously it's appearing at the middle of these 2 and 3, so it looks like it's appearing at 2.5 volt. Look at here. So this transition is taking place at this 2.5 volt. Okay, but this is the 1/2 cycle, or this is the 1/2. That means when the input is changing from the negative to positive. But for the opposite case, we need to change these commands. That means from +5 to -5, and this should be -0. And now if I run, you can see it's appearing exactly at -2.5 volt, and as expected this one. Now how I can plot these two data simultaneously to get the hysteresis plot? So here it's very simple. So first of all, I'm going to file, export data as text. So this is the V0 I'm exporting, and I'm going to negative to positive. Okay, and next one is the opposite case that already I have shown you, that -5 to +5. In a similar way, file, export data, V0, okay, right now we got them. Now I'm going to open this plotting software, Views. Views is a free and open source software for plotting, obviously scientific plotting, obviously, and you can have any kind of scientific plotting, and you can use this software for your publication event. I have used during my PhD. So trust me, it's a very nice and very beautiful software. And if you want to compare this software with the commercial one, that means the origin, if you will find that this software is really too good as compared with the origin. And you can download it freely. It's available for Windows, for Mac, as well as for Linux also. When you will install the software and run for this first time, it will guide you for the basic steps that I'm going to discuss it over here, and thereafter you can be mastered on this software if you use continuously. First of all, you have a page. This is a default settings. There's a graph, and this graph has a x-y axis, but here you cannot plot. In order to plot, you must have to bring these plots. These are these linear plots, or there are several plots, these point plots. All kind of plots are available on these toolbars. So if you want to plot a particular settings, then you have to click it over there. So as I am interested to plot a point or data point, click this one. So right now this appears, one data point plotting appeared under this graph. So now I'm going to import my first data. So this one is the import. I'm going to import, and here I'm going to get the data. Our first data set was data negative to positive. So this one I'm opening, and look at here. You have to mention, since it has a 2 columns and the data was saved in text mode, so you have to mention the 2 column names. So first of all, I'm assuming it's that v-in1 for input and v-0-1 for the output. So v-in1 will refer this column, this one, that means the v3, and v-0-1 will refer this v0. Okay, and importing. So look at here, the data has been imported. Next, I'm choosing the second data set, my positive to negative. Right now, I have to change this name, because if you do not change this, so it will be copied on the previous data set. So that I don't want to do that. That's why I'm doing that thing, and I'm getting the 2 data sets. So first of all, the xy1, this plot I'm going to use to plot my first data set. That means along the x-axis, this is the x data. So along the x-axis, I'm going to plot that v-in1, and along the y data, I'm going to plot these v-0-1. Look at here. But these are not so pretty. So in order to change that, look at here, the markers are by default appearing to this region and this region. So in order to remove this marker, just click over here, none, and I want this line a bit thicker. So this is the line property, and I'm going over there, and this is say 2 point. Okay, so it's good for now. And for the second data set, I'm going to take another xy plot, and for that I'm going to take that v-in2 on the x-axis and v-0-2 on the y-axis. No, here I did a mistake. That is the v-in1. No, it should be 2. Yeah. So look at here. Right now I am having the hysteresis plot. As I have shown you using that animation, the same thing I have obtained over here. So if you find this tutorial is helpful for you, please like, share and subscribe, and click on the bell icon to get notifications for my next video. And please suggest me on different topics if you want me to make videos on those topics. Till then, thank you very much. Thank you for being with me.